This is a presentation of the Land Surface Temperature Monitoring LSTM mission, which is going to be part of the Copernicus expansion missions, so the next generation of the Copernicus Sentinel spacecraft that will provide a further capacity to the European Copernicus Earth observation program. With the Copernicus expansion missions, we will be effectively adding to the capacity that we already have as part of the Copernicus program. So basically from a family of 6 Sentinels at the moment, we will be going towards a family of 12. So basically 6 further missions to add to the Copernicus program. And these are the ones which we call the so-called Copernicus expansion missions, which LSTM is part of, and I will just give a quick overview of the other ones on the next slide. The 6 Copernicus expansion missions will allow us then to contribute to combating climate change, monitoring food security and water management, also monitoring land and natural resources, as well as safeguarding the Arctic. In detail, these missions are then the CO2M mission. Anthropogenic CO2 monitoring is the main objective of this mission. Then we have CHIME, the Copernicus Hyperspectral Imaging mission for the environment. This will allow us to provide services for food security, agricultural management, soil and mineral resources. Then there is the mission SIMMER that has already been presented by Jakob Heuer also here at GRIST, the Copernicus Imaging Microwave Radiometer to provide sea surface temperature, sea ice concentration and extent, sea surface salinity and also soil moisture. Then there is the LSTM mission that is the subject of this presentation, so the Copernicus Land Surface Temperature Monitoring mission, which allows us to provide thermal infrared observations over land and coastal regions for agriculture and urban management services. Then there is CRYSTAL, the Copernicus Polar Ice and Snow Topographic Altimeter. So basically this will allow us to study climate change effects, such as sea ice thickness and snow depth, ocean surface elevation and changes of glaciers. And there is ROSEL, which is a radar observing system for Europe L-band SAR, in support of forest monitoring, agricultural and high-resolution monitoring of the Arctic and cryosphere, as well as to provide services in disasters and geohazards monitoring. So to put LSTM into a context of climate change impact and adaptation, there are several key risks for Europe under low to medium adaptation to climate change, so to global warming. And 3 of these key climate risks are addressable directly by LSTM. We have the human heat stress mortality and morbidity. Then there is losses in crop production and also water scarcity in southern Europe as well as also in western and central Europe, which is becoming ever more a problem in recent years. The LSTM mission objective is to provide high spatiotemporal resolution thermal infrared observations over land and coastal regions in support of agricultural management services and a range of additional applications. So to have precise estimates of biomass as well as evapotranspiration will give us a very good handle on water resource management. In terms of the actual mission, the contract to build the mission has been signed with Airbus Spain as the prime of a large consortium. The budget for this is 380 million euros for 2 LSTM satellites, and the LSTM phase B2 started on the 24th of November in 2020. The defined baseline design for the mission leads to a satellite of about 1.1 tons weight and an instrument size of about 1.5 times 1.5 times 2.5 meters. The mission concept is based on a constellation of 2 spacecraft, where each satellite has an orbit of around 640 kilometers of altitude and a swath of roughly 700 kilometers. The maximal observation zenith angle is 30.8 degrees. And the local time of observation at 45 degrees latitude over Europe is 13 hours. The geometric revisit of each satellite is 4 days, so that we have a geometric revisit of 2 days that can be achieved with 2 satellites. The acquisition system is a whisk broom concept, so it's a scanner mechanism that swipes the swath about every 5 seconds, projecting the ground image onto the instrument, on the Vernier sphere and also the TIA focal planes, that are controlled respectively at ambient cold and cryogenic temperatures. The in-flight calibration is achieved for the different focal planes through the use of black bodies, sun and cold and space views. The spatial resolution is 30 to 50 meters to match European field scale variability. LST observations should optimally be acquired daily. This is the goal, with a minimum threshold of 3 days. The LST over all land surface with an uncertainty of 1 Kelvin, that is the goal, to 1.5 Kelvin as a threshold is the main objective of the mission. We have 5 thermal bands for LST emissivity separation, and simultaneously there is a need for vis, near and sphere observations in 6 bands required for atmospheric correction, cloud detection, and also emissivity estimations. LSTM applications and services are largely driven by water productivity for sustainable agriculture. So basically to provide accurate evapotranspiration maps in support of water resource management, and also for urban planning in terms of urban heat islands. So here you can see some acquisitions by the eco-stress instrument on the ISS of Milano and Paris from the last years. And these are the typical type of data that in terms of spatial resolution, as eco-stress has roughly the same than LSTM, that we will expect, or that we are expecting from the LSTM mission. The LSTM data product as well as latency foresees first of all at level 1C. We are aiming to provide the radiometrically and geometrically calibrated TOA radiance. This is still a slight TBD because we are also in discussions to provide a reflectance instead of radiance, and also for the thermal bands, the top of atmosphere brightness temperatures. At level 2, as in the so-called level 2A product, we will provide the land surface temperature, land surface emissivity per thermal spectral band, the bottom of atmosphere surface reflectance, the total column water vapor, as it is an intermediate product required for the LST retrieval, as well as a cloud mask, which is also again an intermediate product provided as a quality flag. And we will be aiming for a maximum data latency for the level 1C of 3 hours. This is the goal with a 6-hour threshold. The highest priority will be over Europe and Africa. And level 2A will be 6 hours to 12 hours. Again, the highest priority being over Europe and Africa. In order to support the early mission CalVal and also algorithm development, there have been some airborne campaigns that were run with the objectives of first of all supporting the LSTM, SPG and also Trishna missions, to provide directionality experiments, to provide urban and nighttime overflights, also to provide links to the GeoX liaise and methane campaigns, then coordinated eco-stress acquisitions, and also fostering open data policy to provide the data also for community exploitation. The campaigns in detail were in 2021, July and August, a HITES instrument campaign in UK and Sweden, and a TASI instrument in Spain. In 2023, May and June, there was a campaign in Italy and France with 2 airplanes that were respectively flying the HITES and OWL instruments, looking at the same target from different angles to study directionality effects. The airborne campaign in the UK in 21 was flying over Milton Keynes. There were 3 sets of parallel lines, one along the solar principal plane, then one along the perpendicular to solar principal plane, and one along the LSTM proposed orbital path. So the parallel lines designed to have measurements over target at nadir, also at plus minus 6 degrees, plus minus 12 degrees, plus minus 15 degrees, and plus minus 18 degrees of the viewing zenith angle. And the requirements were completely cloud-free conditions. And this provided an extremely valuable data set to study thermal directionality. Now here the planning for the LSTM space segment. So the LSTM phase B2 kicked off end 2020. There was a preliminary design review in Q2 2022, so this is concluded. Then there is a critical design review planned for Q4 2023, so quite soon. And the prototype flight model will undergo a QAR at the end of 2028. Here you can see a simulation of the two LSTM spacecraft and how they will obtain the global coverage of revisit time in 2 days. So the MLST is going to be 1230 at the descending node. The altitude is roughly 650 kilometers. We have a subsampling distance of 50 meters, 37 at nadir, and we're aiming for a geolocation accuracy of 25 meters. The elevation angle is 27.7 degrees, and the maximum observation zenith angle will be roughly 30 degrees. The LSTM acquisition mask foresees then that we perform systematic acquisitions over land and inland water located between minus 56 degrees latitude and plus 83 degrees latitude, as well as archipelagos and also insular areas. And then all coastal waters up to 100 kilometers from the shore, all islands greater than 100 square kilometers with a 100-kilometer coastline, as well as the Mediterranean Sea and all closed seas, so for example the Caspian Sea as well as also the Caribbean Sea. And under investigation is also to increase the acquisition mask to include Antarctic coverage. The instrument design is based on a whisk broom acquisition concept, with a total swath of 727 kilometers swapped in 4.5 seconds, with a useful swath at the end of 670 kilometers. The instantaneous field of view is 29.3 kilometers times 39.4 kilometers, and you can see up here also an illustration of the sequence of the scan from throughout the swath, as well as then via the deep space cold calibration, as well as the black body hot calibration within one scan. LSTM is designed to have 11 spectral bands, 1 aperture and 3 optical paths. There's an onboard calibration to provide a deep space port as well as a black body. The MTF is aiming to be around 0.2 to 0.3. The NEDT the objective is to be less than 0.15 Kelvin at 300 Kelvin, and the absolute radiometric accuracy 0.5 Kelvin. We have 4 near bands, visible and near, so for 90 micrometers, 665, 865, and 945. Then we have 2 sphere bands, 1 380 micrometers and 1.610 micrometers. Then we have 5 thermal channels, 8.6 microns, 8.9 microns, 9.2 microns, 10.9 microns, and 12 microns. The industrial consortium to build the mission consists of Airbus Defence and Space Spain, SAU Spain. As said, they are the satellite prime with about 30 lower level subcontractors for the platform units and the system support. They're heavily supported by Airbus Defence and Space Germany for the platform engineering and also procurement for some common units. The instrument prime is Airbus France, also again with about 30 lower level subcontractors for the instrument units. Within LSTM, we're heavily seeking for international collaboration, especially in view of the Trishna SPG and LSTM mission all being there at the same time. We are really looking into 3 missions that can be harmonized as one in terms of a long data series and also in terms of benefiting from all 3 missions to improve our revisit, so to have basically up to daily coverage. There will be a lot of synergies between these 3 missions in terms of product harmonization and also ATBDs. The orbit coordination also to ensure intersection of the flight lines, inter-flight inter-comparisons, also inter-calibration potentially, common Cal-Val approaches that we are starting to discuss already since a while now, as well as airborne campaigns that will be beneficial to all 3 missions. Thank you very much for your attention, and I'm open to any questions.